Hey everyone, have you ever wondered how we teach a computer to make a prediction? To look at a bunch of information and guess a price, or a score, or even a simple yes or no. Well, today we're going to crack open the foundational toolkit for doing exactly that. And it all starts with one big question. Really, it all boils down to this. No, this isn't about some kind of magic crystal ball, right? It's all about finding patterns in the data we already have. And the way we do that is with a set of really powerful but understandable mathematical tools. We're going to build up your understanding of these tools one simple idea at a time. Okay, so our very first tool is the absolute workhorse of machine learning, linear regression. And you know what? The core idea here is super intuitive. If you just imagine a whole bunch of data points scattered on a graph, linear regression is really just about drawing the one single straight line that best slices right through the middle of them. So what kind of problem does this actually solve? Well, it's all about predicting a number, something continuous. Take this example. As someone's years of experience go up, what do we expect to happen to their salary? We can kind of see a trend there with our eyes, and linear regression is the tool that finds the exact mathematical line to describe. The way the model does this is with something called a hypothesis function. Now, don't let that name scare you. Seriously, it's just a recipe. It's like saying, okay, take the years of experience, multiply it by some number that represents its importance, maybe add a starting value, and boom, that's your predicted salary. The whole game is just finding the perfect weights for our ingredients. But how does it know which line is the best one out of all the possibilities? Well, the goal is to make the error as small as possible. The method for this is called least squares. Think of it this way. It measures the distance from every single real data point to our line, squares those distances to make them all positive, and then it tries to make that grand total as tiny as it can be. The line with the least total squared error wins. Simple as that. And the process for actually finding that winning line is an amazing algorithm called gradient descent. Okay, imagine you're standing on a foggy hillside, and you want to get to the very bottom, the lowest point. You can't see the whole valley, but you can feel which way is downhill from where you are. So you take a small step in that direction. You check again, and you take another step. That is exactly what gradient descent does. It starts with a totally random line, measures the error, and then just nudges the line step by step in the direction that makes the error smaller until it literally can't go any lower. So a straight line is awesome, it's a great start. But what happens when the relationship in our data isn't that simple? What if the pattern has a curve to it? This is where our first tool just can't keep up. To handle these kinds of situations, we need something a little more flexible. We need polynomial regression. And you can really see the difference here. With a linear relationship, right, the output goes up by the same amount for every step the input takes. But with a polynomial one, that rate of change can change. To capture this, we basically give our model new ingredients. We take our original input, let's call it x, and we also give it x squared and maybe even x cubed. This gives the model the power it needs to bend its line and fit that curve perfectly. Now, having a more powerful, more flexible model, that sounds amazing, right? But with great power comes, well, a great danger. And this danger has a name. It's called overfitting. It's basically what happens when your model gets a little too smart for its own good. This quote right here just nails the problem. If we let our model get way too complex, using all those high-powered terms, it can end up drawing this absurdly squiggly line that hits every single one of our data points. But when it does that, it's not actually learning the real underlying pattern. It's just memorizing the random little jitters, the noise that exists in our data. So here's the bottom line. An overfit model looks like an absolute genius on the data it was trained on. But the moment you show it some new data it's never seen before, it fails completely. It's like it memorized the answers for the test instead of actually learning the subject. So how do we fight this? How do we stop our model from going wild? We use a brilliant technique called regularization. The best way to think about it is like a leash. It lets the model be flexible, for sure, but it adds a little penalty every time it tries to make its weights, those recipe ingredients from before, too big. This basically encourages the model to find a simpler, smoother curve that captures the general trend, not all the noisy distractions. All right, so far we've learned how to predict numbers that can fall anywhere on a line or a curve. But what if the question we're trying to answer is totally different? What if the answer isn't a number at all, but a choice, like yes or no? For that kind of job, we need a brand new tool in our kit. And this right here is a fundamental split in machine learning. Everything we've done up to this point is called regression, predicting a continuous value, like a house price. This new type of problem is called classification, predicting a distinct category. For example, is a customer going to stay with our service or are they going to churn? It's a yes or no question. The secret sauce that makes this all work is a really clever piece of math called the sigmoid function. Our model still kind of calculates a score, just like it did before. But then it pushes that score through this cool S-shaped function, and no matter how big or small that initial score is, the sigmoid squishes the output so it always lands somewhere between 0 and 1. And what's that? A probability. So how do we get our final yes or no? We just set a really simple threshold, usually right at 0.5. If the model's probability is more than 0.5, we predict yes. If it's less than 0.5, we predict no. That's it. This simple line in the sand creates the decision boundary between our two choices. And just like that, you've been equipped with 3 of the most foundational tools for making predictions with data. So let's take a quick look at the awesome toolkit you've just put together. So here it is, your toolkit at a glance. When you need to predict a number, your go-to starting point is linear regression. If you spot a curve in the data, you can upgrade to polynomial regression to handle it. And if your problem isn't about numbers at all, but about sorting things into yes or no buckets, you now have the perfect tool for that job, logistic regression. These 3 models, they are truly the bedrock of so much of our modern data-driven world. So I have a final question for you. Now that you understand how we can find straight lines and curves and decision boundaries in data, what patterns are you going to start seeing? What relationships will you look for in the world around you? Thanks for tuning in.